Alright, so our first problem says that an object's velocity as a function of time in one dimension is given by this equation right here. So the equation is x of t equals 12t minus 8e to the 0.25 t plus 8. That's our equation. And it's asking us what is the object's velocity between 0 and 5 seconds. So it's asking for average velocity, so we're going to use the equation for average velocity, which is delta x over t, and this can also be written as velocity final minus not velocity, position final minus initial position over time. And so we have our equation. Now we just have to plug in our variables. We're going to get this final position and initial position once we plug in our times into this equation. So our times are, we start at 0 and then we go to 5. So our final position is going to be at 5 seconds and our initial position is going to be at 0 seconds. So let's plug that in. Alright, and then once you plug that into the calculator, you should get, for 5 seconds, it's going to be 40.077 meters, and then for 0 seconds, it's going to be 0 meters. And then with these values, you're just going to plug them into the equation that we have. So then that's x final, which is this one. It's going to be 40.077 minus x initial, which is 0, over the time. The time is just going to be from 0 to 5. So that's just going to be 5 seconds. And then once you plug that in to the calculator, this is really just that. Once you plug that in, you should get 8.0154. Round that to 3 significant figures, you'll get 8.02 meters per second, and then that's going to be your final answer. The next question is asking us, what is the object's instantaneous velocity at time equals 5 seconds? So instantaneous velocity is going to be, to get the equation for instantaneous velocity, we're going to have to take the derivative of position, the position function. So the first derivative of our position function is equal to our velocity function, which is equal to, now we take the derivative of this, so the derivative of 12t is just going to be 12 minus the derivative of 8e to the 0.25. That's going to be with the chain rule, so that's going to be e to the 0.25t multiplied by the inside, multiplied by the derivative of the inside, which is just 0.25. If we bring that to the front, that's going to get multiplied with the 8. So then there we'll get 2e to the 0.25t. And since this 8 at the end is just a constant, that's just going to be 0. So that's just going to be 0. And then now since it's asking what is the instantaneous velocity at 5 seconds, we're just going to plug 5 into our new into our new equation for velocity. So v of 5 is going to be equal to 12 minus 2e to the 0.25 times 5. And that should get you 5.0193. And then you round that, you're going to get 5.02 meters per second. That is your answer. And then the next question is, we're going to leave this equation because we're going to need it. So the next question is asking us, what is the object's average acceleration between 0 seconds and 5 seconds? So this is going to be the same as the first problem that we did, just not now we're looking at average acceleration instead of average velocity. So we're going to use a very similar equation, which is going to be the average acceleration is equal to the change in velocity over time, and that could be rewritten as velocity final minus velocity initial over time. And again, we're going from 0 to 5 seconds. So at 5 seconds is going to be our final velocity, and then at 0 seconds is going to be our initial velocity. So now we just plug in these times into our velocity function. So it's going to be v of 5 equals 12 minus 2e 0.25 times 5, and then v of 0 equals 12 minus 2e 0.25 to the 0.25 times 0. And then there you're going to get, for 5 seconds, we're going to get 5.0193. And then for 0 seconds, we're going to get 10. And then now we're just plugging these values over here again. So it's going to be the final velocity minus the initial. So it's going to be 5.0193 minus 10 all over the time, which we're going from 0 to 5. So that's just going to be 5. And then once you plug that into the calculator, you are going to get negative 0.9961. And then you round that, you get negative 0.996 meters per second squared. So since we have a negative acceleration, that means that this object is slowing down. And we can also see that because its initial is 10 and then its final is 5. And then the final question for this, the final part for this question is, what is the position of the object when its instantaneous velocity is equal to 0? So to do this one, to do this last one, we're gonna need the velocity equation. So it's asking us, what is the position of the object when its instantaneous velocity is equal to 0? So the first thing we want to do is we want to set this equation here equal to 0. So that's going to be 12 minus 2e to the 0.25 t equals to 0, and we want to solve for t. So the first thing that we're going to do is we're going to subtract by 12. That's going to get us negative 2e 0.25t equals negative 12. Then we're going to divide by negative 2. Now we have e to the 0.25t equals 6. And then to get rid of this e, we're going to multiply both sides by the natural log. We're going to take the natural log of both sides. So that cancels out. So now we have 0.25t equals the natural log of 6. Now we just divide by 0.25. And then your time should be equal to 7.1670 seconds. And then now with this, we're gonna go and since it's asking us what is the position when our velocity is equal to 0, we found our time when our velocity is equal to 0, which is this one. Now we're gonna plug in this time into this equation to get our position. So we're gonna do x of 7.167 . And then that should get you 46.004, or if you round, 46.0 meters. And that's going to be your final answer. Okay, so then our next problem says that an object has an initial velocity of 30 meters per second in the I direction. I direction is just the same as the X direction, and comes to a stop over a time of 8.5 seconds. And then the first part is asking what is the object's constant acceleration. So the first thing that we're gonna do is we're gonna write down everything that we're given. So the initial velocity, so velocity initial in the X is 30 meters per second. And then it says that it comes to a stop, so that's gonna tell us that the final is gonna be equal to 0 meters per second. And then we're given the time, which is 8.5. And then we're asked for acceleration. So we have 3 variables and we're looking for 1 for acceleration. So we're going to use the equation, this equation. So velocity final equals velocity initial plus acceleration times time. And then all of these are vectors. So we're looking for acceleration. So we're going to rearrange this equation and isolate acceleration. So we could subtract vi. And then we want acceleration by itself, so we could divide by t. So then we get that acceleration is equal to velocity final minus velocity initial over t. And since we already have all of these values, now we're just going to go ahead and plug them all in. So acceleration equals the velocity final, which is 0, and then minus the velocity initial, which is 30, all over the time, which is 8.5. And that should give you, when you plug that into a calculator, you should get negative 3.5294. And if you round, you get negative 3.53 meters per second squared as your final answer. So that one is going to be your final answer for that part. And then the next question is asking us what is the total distance that the object travels when it comes to a stop. So we're going to keep the acceleration, but we're going to keep the top one so that our answers could be more accurate. That's on mine. Erase this. So now we're looking for the displacement, and we're going to use, since So now we have 4 variables and we're looking for displacement. We're going to use the easiest equation, which is just delta x equals velocity initial times time plus 1/2 at squared. All right, and then from here, we're just gonna, pretty straightforward. Hold on. We're looking for delta x. So now we're just plugging everything and then we should be able to get delta x. So delta x equals the velocity initial, which is 30, and then times the time, 8.5, plus 1/2 the acceleration. Not 8.5. The acceleration is negative 3.5294, and the time squared, which is 8.5 squared. And then that should give you not 127.5 meters. And that is your answer for part B. And then the next part is asking, what is the speed of the object after traveling a distance of 25 meters from its initial location? So we're going to keep all these variables. Well, we're going to keep all these variables except the delta x. Now we have a new delta. Now we know what delta x is. It's going to be 25. And then I guess it's the time could go as well, because we're gonna have a different time. Although we're not solving for time right now, we're gonna have a different time in this case. So everything there's good. So now what we're looking for is, what is the speed of the object. So we're looking for final velocity. Final velocity is also not gonna be 0. Final velocity is gonna be what we're looking for. So looking at our equations, the easiest one that we're gonna be able to use is this one. So it's going to be velocity final squared equals velocity initial squared plus 2a delta x. And I'm going to go ahead and rearrange it just so that it gets simpler. So it's just going to be v final equals the square root of vi squared plus 2a delta x. And then now you just plug in all the variables. So the initial is 30. So that's 30 squared plus 2. The acceleration is negative 3.5294. And the displacement is 25. And then once you plug that in, you should get that velocity final is 26.898, or if you round it, it's 26.9 meters per second in the I-hat direction. And then the last part is asking us, what amount of time does it take the object to move a distance of 40 meters from its initial location? So now we're looking for time. So erase all this. Now we don't know velocity final again. We have a new displacement, and then we're looking for time this time. And our new displacement is going to be 40. So then we're looking for the time. So we're going to use this equation right here. It's going to be delta x equals velocity initial time plus 1/2 at squared. Now, since t is going to be what we're looking for, but we have a t right here and then a t squared right here, we this is going to be a quadratic equation. So we just move the delta x over to get, and then set all of this equal to 0. And then I like to rearrange it so that it's like a, b, c. So it's going to be 1/2 a2 squared plus vit minus delta x. And then now you plug in your variables, so it's going to be 0 equals 1/2 negative 3.5294 squared plus velocity initial, which is 30 times t, minus delta x, which is 40. And then this is going to be your A, that's going to be your B, and that's going to be your C. And then this whole thing, so this whole thing is going to be your A, so 1/2 times the acceleration is going to be your A. And then once you plug that into the calculator, you solve for plus. When you're doing negative b plus, you're going to get 1.4584 seconds. When you're doing negative b minus, you're going to get 15.541 seconds. Now, technically, both of these are right. Both of these are right, but we're gonna do the first one because let's say we have like a ball. Let's say this thing is a ball. So it was first going. It started here, and then what this time is for what the 1.4 seconds says is that it was moving, and then after 1.4 seconds, the displacement from here to here was 40 after 1.4 seconds. And then the 15 is saying that it went from all the way, like, I don't know, like all the way over here. And then since we know that the acceleration is negative and the initial was positive, we know that this object was slowing down. And then it's eventually going to change direction. So then it's going to start going back. And then at some time, well, at 15 seconds, it's going to be right here, which is the same as this one, which is the same as 40 meters. It's the same, but the 15 is just when it already turns around, and then the 1.4 is when it's going for the first time. So, professor used this time. So, I guess we only care about when it's going the first time. Okay, so then moving on to the next question. Question number 3, we have two objects are initially at the same location. Object 1 has an initial velocity of 8 meters per second in the I direction and undergoes a constant acceleration of 2 meters per second in the I direction. So let's write that down. So we have object number 1's velocity initial for number 1 is equal to 8 meters per second, and it has a constant acceleration of 2 meters per second. So and then object number 2 is initially at rest and undergoes a constant acceleration of negative 3 meters per second in the I-hat direction. So object number 2 is its initial velocity is going to be 0, and then its acceleration is going to be negative 3. And then now it's asking us for part A, it's asking us what is the distance between the objects at 10 seconds. So at 10 seconds, so we have two variables, now we have another one, so it's going to be time, which is the same for both of them. And the equation that we're going to use is Since we're looking for distance, we're going to use the simplest equation. So we're going to use this one. And, okay. So yeah, now we're just going to plug in all of our variables for each one of them. And then we're going to find at what position this one is, and then what position this one is. And then we're just going to find the difference between those two positions. So for the first one, it's going to be and that should give you 180 meters. And then for the second one, it's going to be, since the velocity initial is 0, this will cancel out. So we just have 1/2 the acceleration and then time squared. And that should give you negative 150 meters. So now we just find the difference. So we're going to do 180 minus 150. And we're going to end up with the final answer of 330 meters between them. Okay, and then the next question is asking us, the next part is asking us, at what time do the objects have the same speed? So we're looking for, with this one, we're going to be looking at the final speed. So when do these two guys have the same final speed? So V final for 1 is going to be the same as V final 2. And then we're looking for the time. We're looking for the time. So what we can do is, using this equation right here, which gives us V final alone already, we could set, since we know that they're gonna have, well, they're gonna have the same speed, not the same velocity, but we'll still use this equation, the same speed. So we're just gonna take in the magnitude. So we're not gonna worry. So for example, this one's already all positive. This one, we're gonna change it to a positive right now. But since we're just worried about the speed, we're gonna change. That's why we're gonna change the sign. So it's gonna look like this. So we know that V final 1 is equal to V final 2. So let's set these equations equal to each other. So V final 1 equals, we know that V initial over here is 0, so it's just going to be AT, like that. And then now we just start plugging in everything that we know. So V1 is 8 plus the acceleration is 2, T equals, we're not going to include the negative. I'm just going to put 3T right there. And then now we're just gonna get all the t's on one side. So we're gonna subtract by not 3t, by 2t, and then you end up with 8 equals 1t, and then that's just t equals 8 seconds, and that is your final answer. The next question is asking us, at what time are the objects the same distance from their initial location? At what time are the objects the same distance from their initial location? So there's a key word in here. It's distance. So we're not taking into account the direction. We just care about the distance, so the magnitude. So for this one, so we know that delta x1 is going to be equal to delta x2. So we're going to set those two equations equal to each other, and the equation that we're going to use is delta x equals vit plus 1/2 a t squared. And like I said, we know that they're going to be the same distance, so we're just going to set these equal to each other. So we have v initial 1 t plus 1/2 a1 t squared is equal to v initial over here is 0 again, so that just cancels out. So we have 1/2 a2 t squared. So now we have this, and we want to get time by itself. So this is going to be a quadratic equation, but let's go ahead and plug in everything that we know. So we have the initial is equal to 8, bring the t down, plus 1/2, the a is 2 t squared, 1/2 of just the magnitude of this one, so it's going to be 3 t squared. To simplify this, we have 8t plus t squared equals 1.5 t squared. And now we're going to get all of these on this side. So we're going to subtract by t squared and subtract by 8t. So then you're going to get 0 equals 0.5 t squared minus 8t. And then you could put a 0 at the end. That's your A, that's your B, and then that's your C. And then now we plug this into the quadratic equation. And when you use negative b minus, you're going to end up with 0 seconds. And then when you use positive, you're going to end up with 16 seconds. True. But it says other than t equals 0, so we're going to cancel this one out. So then we're just left with 16 seconds. All right, moving on to the next part, we have the question, how much faster is object 2 moving than object 1 when the distance between them is 100 meters? So another key word right here is how much faster. So we just care about the magnitude, not about the directions. So how much faster is object 2 moving than object 1 when the distance between them is 100 meters? So the first thing that we want to do is we want to find the we're going to set up velocity equations for both of these. So we know that velocity final equals velocity initial plus at. This is the equation that we're going to use to set up equations for these. So the equation for this one is going to be v1 t equals velocity initial, which is 8, plus the acceleration t. So this equation right here is going to give you this object's velocity at any given time. And then we're going to do the same over here. So we have v2 equals to, that one is going to become a 0, so we just have acceleration and time. And since we just care about the magnitude, we're going to do 3t. Now that we have these equations, from this, we're going to get position equations. So to get position from velocity, we're just going to integrate. So we're going to, I guess you would integrate that. Here, you're going to get x of 1 t is equal to 8t plus t squared. And usually, we are going to have a plus c, but since it told us that they both started at the same position, it would just be 0. Or, yeah, at the same location. So it'd just be 0, and then the same case for this one. So x2t is equal to 1.5 t squared, and then the c is just going to be equal to 0. And then now what we're going to do, because it's asking us when the distance between them is 100 meters, now we're going to add these two equations and set them equal to 100. So we have 8t plus t squared plus 1.5 t squared is equal to 100. Now we're just going to go ahead and simplify here. So we have 8t plus 2.5 t squared equals 100. And this is going to be a quadratic equation. So let's subtract this 100. So then we have, I'm just going to rearrange it. So we have 2.5 t squared plus 8t minus 100. That's A. This is B. And this is C. And then now we're going to plug that into our quadratic equation. And when you use negative B plus, you're going to get 4.9238. And when you use negative B minus, you're going to get negative 8.1238. And time cannot be negative. So we're going to go with this time right here. So this is the time when they are 100 meters apart. So now what we're going to do with this time is we're going to go and plug this in to these equations, the velocity equations for each of them, to find out what their velocity is at that time. So we have V1 of 4.9238. And then we have V2 and then for this one, for the top one, or for the first velocity, you're going to get 17.847 meters per second. And then for the second velocity, you're going to get 14.771 meters per second. And then now we want to take the difference. So we want to find the difference to see which one is going faster. So this one is clearly going faster, but we're going to see by how much. So it's going to be 17.847 minus 14.771, and you should get 3.076 meters per second, or rounding, you get 3.08 meters per second. And your final answer would be that object 1 is moving faster by 3.08 meters per second when the distance between them is 100 meters. Okay, so moving on to problem number 4, it says that a projectile was launched from a location that is 30 meters above ground level with an initial velocity of 25 meters per second at 57 degrees with respect to the horizontal. What is the object's maximum height? All right, so the first thing that I'm going to do is I'm going to break down this velocity to get the y component and the x component. So we have velocity initial in the y is going to be equal to 25 sine of 57, and then velocity initial in the x is going to be equal to 25 cosine of 57. Plugging that into the calculator for sine, you're going to get 20.966 meters per second, and for cosine, you're going to get 13.615 meters per second. Okay, and then now it's asking us, what is the object's maximum height? So for maximum height, we're gonna use this equation since we don't have time, so we can't use the other one. So it's v final squared equals v initial squared plus 2a delta y, since we're looking at the height. And then I'm just gonna rearrange this equation right now to make it easier at the end. So we're gonna get rid of we're gonna subtract this vi squared. Now we have vf squared minus vi squared equals 2a delta y. I'm going to divide over here by 2a, divide this side by 2a. So then now we get that delta y equals velocity final squared minus velocity initial squared over 2a. And then plugging in all our values, we have velocity final is equal to 0 because at its maximum height is when it's going to start turning around. So its velocity is going to be equal to 0. So we have 0 minus velocity initial is, this is for the y. So we're going to look at the y component. So it's 20.966 all over 2. And then a, the acceleration, and the y. I should have wrote that down. But ay is equal to negative 9.8 meters per second squared. So over here is going to be negative 9.8. And then now we plug that in, we're going to plug that into the calculator. You're going to, sorry. Since this is squared, we have to square this. Square that. And it's just this that is getting squared, not the negative. So then now when you plug that in to the calculator, you should get 22.427 meters, but it's asking for the maximum height, and it tells us in the beginning that it is already 30 meters above ground level. So to this, we're going to add 30. So then your final answer should be 52.427, or rounding 52.4 meters, and that is going to be the maximum height that it reaches. Okay, and then the next part B, is asking us what is the total time that the object is in the air for. Okay, so for that one, the total time that the object is in the air for, so let's write down all the variables that we know. So we have the acceleration of the y is equal to negative 9.8 meters per second squared. What is the total time that the object is in the air for? So we want the time. So let's say the object starts from like right here. That's 30 meters. So we want how long it takes for it to go all the way up and then back down right here. So then the displacement that we're going to use is negative 30 meters because it goes down by 30. So then now we have three variables. We have the velocity initial, the acceleration, and then the displacement, and the y, which is equal to negative 30 meters. And then now we just plug that into, we use this formula, this equation. Delta y equals VIT plus 1/2 AT squared. And since we're looking for time, we're going to see that this is going to be a quadratic equation. So let's rearrange this. So minus delta y minus delta y. And then I'm just going to rearrange all of this to make it easier for me. So 1/2 AT squared plus VIT minus delta y. And then now I'm going to plug in all my variables. So it's going to be 1/2 negative 9.8 t squared plus the velocity initial, which was 20.966 t, and then t minus the delta y, And then the delta y is already negative, so 2 negatives makes a positive, so that's going to be positive 30. And then now we can simplify even more. So we got negative 4.9 t squared plus 20.966 t plus 30. This is going to be your A, that's going to be your B, that's going to be your C. Plugging that into the quadratic formula, you're going to get for negative B minus, you're going to get 5.4103 seconds, and then for positive, for plus, you're going to get negative 1.1316 seconds. And since time can be negative, we're going to cross that one out and go with this one. So that's going to be your time for the total. That's going to be the total time that the object is in the air for, because this is how long it's going to take for it to go from up there all the way to down here. And we're going to save that time because we're going to need it for the next problem. So that's the total time that it's in the air for. So the time is equal to 5.4103 seconds. I guess when you for your final answer to round for this part, for part B, it would be 5.41 seconds. That would be your final answer. But for the next part, we're going to use this one to get a more accurate answer. So the next question is asking us, what is the object's total displacement in the x direction when it reaches the ground? So this one, we're just going to use this simple equation. Delta x equals velocity times time. That's the only equation we have when velocity is constant. So we have all these variables, so let's just go ahead and plug them in. So delta x is going to equal to velocity in the x. So that's 13.615 times the time, which is 5.4103. And that should get you that delta x is equal to 73.668, or rounding 73.7 meters as your final answer. So 73.7 meters is the total displacement in the x when it goes from here all the way to here. So, and then the last part is asking us, what is the object's velocity as a magnitude and direction 2 seconds before reaching the ground? Okay, so 2 seconds before reaching the ground. So we're going to use this time, and luckily we have VIX, and VIX is never going to change, so we don't have to solve for that. We already have it. So we're just going to look for V final Y. So that's going to be we're going to use this formula. So V final Y equals V initial Y plus AT. And for the time, we're just going to do this time minus 2 seconds. So it's going to be V final Y is equal to V initial in the Y. So it's 20.966 plus the acceleration, which is negative 9.8. And at the time, this minus 2 is going to give you 3.4103. And then finally, plugging all of that into the calculator, you should get that V final Y is going to equal to negative 12.454 meters per second. But it's asking us what is the magnitude. So to get the magnitude, we're going to use the Pythagorean theorem. So we're going to do the square root of 13.6615 squared plus the square root of negative 12.454 squared. That's going to get you 18.451 meters per second. So that's going to be our magnitude. Now we need our direction. For the direction, for the direction, you're going to use this formula. So that is going to be equal to arctan of, sine over cosine for y over x. So for y, we have negative 12.454 all over 13.615. And then once you plug that in, you should get negative 42.449. Rounding, you get negative 42.4 degrees. So then your final answer is going to be 18.451 meters per, or if you round that as well, 18.5 meters per second at negative 42.4 degrees. That would be your final answer. Okay, so the next question says, a blue projectile was launched from ground level with an initial velocity of 25 meters per second at 57 degrees with respect to the horizontal. And it's asking us in part A, what is the maximum height of the projectile and the total time it is in the air for. So this one is actually really similar to the one that we just did. So the first thing I'm going to do is I'm going to break apart the velocity. So velocity in the x and velocity in the y is equal to 25. This one is cosine. This one is sine. And then it's 57 degrees. Plugging that into the calculator, you're going to get for sine is 20.966 meters per second. And then for cosine, it's 13.615 meters per second. Okay, and then it's asking us what is the maximum height. So for them to find the maximum height, we're going to use this equation right here. Velocity final squared equals velocity initial squared plus 2a delta y. Delta y because we're looking for the height. So we're looking at the y component. So then now I'm going to rearrange this equation to get delta y by itself. So I'll do minus vs squared equals 2a delta y. Get delta y by itself by dividing by 2a, divided by 2a. So now we have that delta y equals vf squared minus vi squared over 2a. And then now we plug in all of our values. So we have delta y equals vf squared. Vf is going to be, so it's going to be at the top. So that's when the velocity is 0 because that's when it starts to turn around back. That's when it starts to turn around and start going down. So it's going to be 0 minus the initial, which is 20.966 squared all over 2, and then the acceleration for y, I need to write that down. Acceleration equals negative 9.8, and then velocity final is equal to 0. So then now we plug in the acceleration, so it's negative 9.8. And then there, you're going to get 22.427 meters. And since it doesn't say that it starts like already at an initial height, that's going to be your final height right here. So if you want to round that, you'll get 22.4 meters as your final height. And then now it's asking us what is the total time that it is in the air for. So now we're gonna look for time, and now we're gonna look for time. So I'm gonna rewrite that. So delta y is equal to 22.4. To be more specific, 22.427, and then this is going to be your initial in the y, and since it's like it's starting here and then it's going like that, the initial velocity, the final velocity here is just going to be the same as the initial velocity but in the opposite direction. So then we're not going to use this for right now, but we're not going to use this specifically for right now, but then our velocity initial is equal to that, and then our velocity final is equal to negative 20.966. Acceleration is equal to negative 9.8. And then now we can just start solving for the time by using this equation right here. So velocity final equals velocity initial plus acceleration time. And we're going to isolate time. So divide by acceleration. Now we get that time equals velocity final minus velocity initial over acceleration. And then plugging in all the variables that we have time equals velocity final is equal to negative 20.966 minus the initial, which is the same thing, just positive, over the acceleration, which is negative 9.8. You'll get that time is equal to 4.2787, and if you round, you get 4.28 seconds. And that is your final answer. Those are your final answers right here. So that's the maximum height, which is 22 meters, and then the time it takes to, the total flight time is going to be 4.28 seconds. Okay, so then the next part is saying a red object is to be released from rest while at some initial elevation above ground level such that it will strike the ground at the same time as the blue projectile. If the object is released at the same time that the blue projectile is launched, what must its initial elevation be? Okay, so I'm sorry, I erased the time. So we're gonna rewrite the time from the last part, which is 4.2787. That's gonna be our time. We're gonna need this later on, so I'm gonna keep it there. And then so it's saying so both of them are gonna be let go at the same time, and we want them to hit the ground at the same time. So we're looking for how high, but so basically one of them is gonna be going like this, and then the other one is gonna be being dropped from there and then going down like that. So we want them to be dropped, or we want them to be put in motion at the same time and then land at the ground at the same time as well. So we're trying to look for the height right here, the height of this second one. So to do that, we're going to use this equation, which is delta y equals velocity initial time plus 1/2 acceleration time squared. This is for the second object. Okay, so it says that it's gonna be released from there. So like if you drop it from there, its initial velocity is gonna be 0. So velocity initial is gonna be 0. Velocity final, we don't know, and we're not worried about right now. The time is going to be the same as that one, so 4.2787. We're looking for delta y, and we know the acceleration is equal to negative 9.8 meters per second squared. So then now we just plug in all of our variables that we have. We know that velocity initial is equal to 0, so that cancels out. So then we're left with delta y equals 1/2 negative 9.8 t squared, which is 4.2787 squared. Plugging that into the calculator, you're going to end up with delta y equals negative 89.705. And the reason why it's negative is because this is telling us that it's going to fall 89 meters. It's going to fall 89 meters. So if it started here and it's going down here, then it traveled like in the negative direction. But since the problem is asking us what is the initial elevation, we're just going to use, we're just going to change this into a positive. So then your final answer is just going to be delta y equals 89.7 meters. That's going to be your final answer right there. So that's how high it needs to be. That's how high it needs to be in order to land at the same time as the first object. Okay, and then the next part is asking us, a green object is initially 100 meters above the ground level and positioned such that it is directly above the location of the blue projectile's maximum height. What initial velocity must the green object have if it's to collide with the blue projectile if both objects are set into motion at the same time? So basically we have a picture that looks like this. So this is the first projectile. This is the first object. And then we have another one that's going to be dropped directly above this one's maximum height. That's some height right there. And then that's another height. And then we know, so we have this one. We know that this one is equal to 22.427. And we don't know this one. We don't know this height. But we do know that these two heights combined is 100 meters. So to get this height, we're going to do 100 meters minus 22.427 meters, and then doing that you'll get 77.573. So this portion right here is 77.573. So that's going to be the displacement for the green object. So now we're going to write down what we know. So we know that the displacement is going to be equal to negative because it's going to travel down. So it's going to be negative this, negative 77.573 meters. The acceleration is negative 9.8. And then we know that the time, so the time is going to be half of this total time because we want them to collide. Yeah, we want them to collide at the middle. So it's just the time that we're going to use is just going to be half of the total time. So that's going to be 2.1393. And then now from here, we're just going to plug these values into our equation so that we can get the initial velocity. So for this one, we're going to use this equation. So delta y is equal to velocity initial time plus 1/2 a t squared, and we want to get velocity initial by itself. So we're going to subtract by 1/2 a t squared on both sides. So we have delta y minus 1/2 a t squared equals VIT, and then divide by t. So then velocity initial is equal to delta y minus 1/2 a t squared over t. Plugging in all the values that we know, velocity initial is going to be equal to delta y, which is negative 77.573 minus 1/2 of the acceleration, which is negative 9.8, and then the time, which is 2.1393, and then square that. All of this over the time again is 2.1393. Plugging that into the calculator, you should get that velocity initial for the green object is equal to negative 25.7803. Rounding that, you'll get negative 25.8 meters per second. And this is going to be in the y direction, so we'll just write a j. J is the same thing as y. So that's going to be our velocity initial. In order for those two objects to collide, in order for the blue and the green projectiles, the blue and the green objects to collide. Okay, and then the next part, it's telling us a rocket is to be launched from the ground at a location directly above where the projectile's maximum height will occur. If the rocket leaves the ground with an initial velocity of 70 meters per second and accelerates upward at a rate of 8 meters per second squared, how long after the projectile is launched should the rocket leave the ground if it is to collide with the projectile? Okay, so we have a similar problem. So we have the blue projectile, which is right here, and then we have like a rocket that's gonna go up here, and we want them to crash right here when the blue one is at its maximum. So to do this, we are gonna use the time that we used in the last part. So we're gonna use this time. So we're not gonna use this one anymore. That's the time for the whole flight. Now we're gonna use the time for half of the flight, or in other words, the time when the blue projectile is going to be at its maximum height. So that's 2.1393 seconds. Okay, so now we're going to write down our variables that we know for the rocket. So for the rocket, we know that the velocity initial and the y is going to be 70 meters per second, and then that the acceleration is 8 meters per second squared, and the delta y, we want it to collide right here at the top. So the delta y is going to be the same as the maximum height of the blue projectile. So it's going to be 22.427 meters. And it's asking how long after, so it's asking for time. So we're going to be looking for time. So time, that's what we're going to be looking for. And for this one, we're going to use the equation delta y equals velocity initial time plus 1/2 a t squared, where this is going to be a quadratic equation since we're looking for time. So let's rearrange that. So minus delta y, and we have 0 equals, I'm just going to rearrange it to make it easier for me, 1/2 a t squared plus vit minus delta y. And then we're going to go ahead and plug in all of our variables. So 1/2, we know the acceleration is equal to 8 t squared plus velocity initial is 70 t, and then minus the delta y, which is that 22.427. 0 is equal to 4t squared plus 70t minus 22.427. That's going to be your A, that's going to be your B, and that's going to be your C. Now you just plug that into the quadratic formula, and for when you do negative b minus, you're gonna get like negative 17, but again, time can't be negative. And when you do negative b plus, you're gonna get for the time you're gonna get 0.3147 seconds. So that's how long it's gonna take the rocket to go from here to here. And we know that the projectile, it's going to take it 2 seconds. So we're going to find the difference. So now we're going to do, so now we're going to do 2.1393 minus the time that we got, 0.3147. and then that should equal to 1.8246. Rounding, you get 1.83 seconds. And that means that the rocket should be launched 1.83 seconds after the projectile, because the rocket is gonna be there really quickly, so it should be launched 1.83 seconds after the projectile.